Welcome to the video. This growth rates for sequences. Yeah. All right. No playing now. We're going to talk about these growth rates. Let's take a look at them. Okay. Let's let the two sequences, A sub k, got it right here, and B sub k, be two sequences where the terms in the B sub k sequence grow faster than the terms in the A sub k sequence. And that's as the index k goes to infinity. So B sub k is growing faster, eventually, somewhere. Could be for index k is 1 billion. Eventually, in the long run, as the index goes to infinity, what we're saying is the sequence B sub k, those terms are growing faster. If we have those assumptions, then what we're going to write is this right here, and that is the terms in the sequence A sub k grow slower than the terms of B sub k sequence. So this little, it's almost like a double inequality, if you will, just means that the terms in A sub k sequence grow slower, that's the big thing, than the terms in the B sub k sequence. And this, of course, is as k goes to infinity. So it might not happen for the first 5 trillion terms or whatever, but eventually, in the long run, B sub k dominates, is what we're saying. Okay, so that's the symbolic representation. And under these assumptions, saying all this stuff is true that we've said so far, then this is what we're going to say. Okay, we're going to organize all the different sequences in order. But first of all, we would say that the limit as k goes to infinity of A sub k over B sub k is 0. Now remember, we're assuming that the terms in A sub k are growing slower than the terms in B sub k. So as k gets very, very large in the input direction, super big towards infinity, then B sub k is going to dominate. It's going to grow so fast compared to A sub k. It's going to get so large that the terms in A sub k can't keep up. And for that reason, B sub k just becomes gigantic, and A sub k eventually just dwindles away. And so therefore, that limit of A sub k over B sub k should be 0. We should keep in mind that we're not really considering the signs of the terms right now. So really just keep in mind that if it's plus or minus, depending on what the terms are doing, it might be that one sequence is going to a big giant positive or giant negative number. And so keep that in mind. Regardless, in this situation, it's still going to be true that this limit's going to be 0. And what if you switch it up? What if you switch the order here? Now the giant big old B sub k is on top, getting big as k goes to infinity. And so A sub k is doing its thing. It's getting bigger, but eventually B sub k grows much, much faster. And therefore, because B sub k dominates still, as we're assuming, if you took the ratio of B sub k over A sub k, then that limit as the index goes to infinity is going to be 0 because the top just dominates there. All right. So there's nice conclusions. Basically, the idea is if we knew something about the relationship with the growth rates between the sequences A sub k and B sub k, as we're assuming, and then you took the limit of the sequence was a ratio of the two sequences, then we could just say immediately, without having to do any real computational mathematics, boom, it's either 0 or infinity, depending on the ratio. Now, let's list these things. What kind of functions we got? What kind of crazy old growth rates going on here? Okay, for the sake of what we're about to say, let's say that P, Q, R, and S, they're all positive real numbers. Okay, so positive real numbers. And then there's going to be this other variable sitting around. We're going to say B. We're going to say that that number is a real number that's bigger than 1 for the sake of the discussion. Okay, So under all these circumstances, let's dissect this statement here. Essentially, this orders the growth rates of different types of sequential functions from smallest to greatest. And, you figure you got a natural log function way down here at the bottom. And then natural log function, of course, grows pretty slow. It's concave down. So it's increasing at a decreasing rate. And if I raise that to some power, it's still going to be concave down. So it ends up that any power of a natural logarithm, that's basically the slowest that we're going to grow in terms of growth rates for all the functions that we're listing here. So we're saying from the first sequence to the next sequence, k to the p, keeping in mind that q and p are just some positive real numbers, they could be anything. Then what we're really saying in this statement right here is that power functions grow faster in the long run than powers of logarithmic functions. Okay, so p could be 1 and q could be 1 billion. Eventually, in the long run, that power function k to the p is going to grow faster than some power of a natural logarithmic function. Moreover, if I then take that same power function k to the p and I multiply it by any power of a logarithm, say the rth power of the natural log, so r could be bigger than q, could be smaller than q. And what we're saying here is that if I then take that power function and multiply it by a power of a logarithm, that's going to grow faster than just the straight up power function. And in fact, that's going to grow faster than any power of a logarithm. Again, in the long run, as k goes to infinity. Keep going. What about this fourth sequence here, k to the p plus s? Again, keeping in mind, p, q, r, and s are all positive real numbers. Then what we're saying here is that, well, we've already established what p is in the previous sequences. If I then make it a little bit bigger, no matter how much, right? S is a positive real number. Then if I have a bigger power of k, then compared to k to the p, then that power function grows faster than the previous three sequences. And so that is, at least from the fourth one to the third one, just pretend k cubed, right? And maybe p is 2 and s is 1. Then what we're saying is that's going to grow faster than just the sequence k squared and then any power of a natural log multiplied with that. So as long as you increase the power of the power function, it's going to grow faster than the product of a power function times the power of a natural logarithmic function. And then you start getting into more heavy-duty types of functions, right? Like this one here. Really, that's a geometric sequence. But if you think of it in terms of real value continuous functions, it's like an exponential function. So you consider any base here bigger than 1, right? So we're growing exponentially. B is 5. B is 1.2. B is pi. That is going to grow faster than any power function, any logarithmic function, and any product of those types of functions. It just grows much, much faster. And then we got the factorials, right? So k factorial, remember, k factorial is like saying k times k minus 1, k minus 2, dot, 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 all the way down to 3 times 2 times 1. And so that grows even faster than an exponential function. For instance, if you consider 4 factorial, that's 4 times 3 times 2 times 1. So what is that? In this case is 24. But what about 5 factorial? As you increase the index k, you're going to multiply that next, you're going to multiply the previous term by the next k. So 24 times 5 for 5 factorial, 24 times 5, right? 120. So that grows faster than an exponential function because the exponential function is always multiplying the previous index by the same ratio, b here. And then finally, the winner of them all, k to the k. So consider that sequence that's 1 to the 1, 2 to the 2, 3 to the 3, dot, 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 and so on. Eventually 50 to the 50th power. That grows so fast. Eventually it gets so gigantically large. You have more in magnitude than the number of atoms in the universe. Just gets just massively large very quickly. So that is the fastest growing of them all. And this is your little list of functions that are at least one-to-one in the sense that we're monotonically increasing. We're not considering some type of sequence that's oscillating or something like that, or alternating, and we're just considering these ones right here. So the whole idea is, well, why is this true? Well, we just talk about it, kind of think about why it's true the way they behave. But, you know, you think how you could show this is true. Well, take limit as k goes to infinity of these arbitrarily defined functions, and then you use concepts of like L'Hopital's rules, things like this. You could show it's true. But this is not a video on the proof. It's a video on trying to argue why it might be true and trying to conceptualize what the idea is. And so the whole point of this is eventually you have a sequence, and if it's a ratio of sequences of these forms, we don't take the actual limit. We just say, look, we know we've established these facts about growth rates, and then we just say, boom, the end. That limit's either 0 or infinity, depending. So let's take a look at a couple of problems here to help us get this down. Okay, for instance, keep that growth rate thing up there. Okay, what if you had a sequence, 7 to the k over k factorial? We said, does that sequence converge or diverge? In other words, we're trying to figure out what's limit k goes to infinity of 7 to the k over k factorial. Well, we just wrote above. If you have k factorial, well, that's one of the fastest growing of them all, right? The only thing that grows faster than that is k to the k. And so hence, 7 to the k is like a b to the k up there where b is 7. And so k factorial grows faster than that in the long run. And hence, because of that, this is just going to be 0. So converges to 0 because in the long run, as k goes to infinity, k factorial grows faster than 7 to the k. You have the little list down here to remind us as well. How about k to the 6 over the natural log of k raised to the 9,000th power? Change that 9,000th power to the 5 trillionth power. Don't matter, right? What we're saying is we got power function of the form k to some power, positive power here, that's a real number. And then at the bottom, we have some power of a natural logarithm. In this case, 9,000th power. Well, any power function in the long run grows faster than any power of a natural logarithm. And for this reason, the numerator there in that sequence is going to eventually overtake the denominator. It's going to grow much, much faster. So, therefore, limit k goes to infinity, k to the 6 over natural log 9,000 k, in other words, natural log of k raised to the 9,000th power. Because the numerator grows faster in the long run, this is just going to be going to infinity. So that's the idea. If we could establish these facts, which I'm trying to convince you of, though it's not a proof, then when you have such types of limits involving sequential functions, you don't actually have to, do some crazy mathematics. You just say, the end, based on the growth rates, I can conclude this or that. But it's got to be of a specific form where it's a quotient of these functions that we see in the list of growth rates. So, that's the growth rate video. I hope it make you grow intellectually. Ha ha ha. Anyways, gonna keep making more videos. And so, I hope you're interested in math and you keep listening to the videos. because it's about to get all twisted. So there you go. The end. Until the next video. See ya.